Okay, we're gonna start class a little bit differently today. How many of you are in chapel? Okay, all right. If you were in chapel, you know what went down in chapel today. Okay, do we want him to give a speech?
What? Okay. Hey, Nate. What? I really appreciate having all you guys as friends, because having strong running makes studying and doing well in classes infinitely easier.
Let's go.
So I've been fortunate enough to have a lot of really strong friends to run with. So thanks for running with me.
Oh man. Okay. Well, now that I don't need coffee, I just need to do stuff like that. Okay. Alrighty. Orthogonal projections. Let's get this going. And then I would particularly stick around at the end of lecture because there's some information. Okay.
Easter eggs. Post-grade. I have a test to get to. Guess what, guys?
A set U1 through UP is an orthogonal set. Is an orthogonal set. You know, I should have worn a shirt that was long enough. If it is I totally wrote the wrong word. That's really funny. Okay, so an orthonormal, sorry. Orthonormal. I thought something was wrong because I was like, it's an orthogonal set. An orthogonal set is an orthogonal set.
In fact, that's accurate.
Yes, actually, it would technically be accurate.
Can I definition?
Can the proof from the exam prove an orthogonal set is an orthogonal set?
It's obvious.
Okay, we did this definition last lecture. What makes it orthonormal?
Unit vectors.
Unit vectors. Yes, a set of unit vectors. Okay, and then, so this is just, I'm putting this here to review it, even though we already lectured on it. And then we could talk about this as a basis for some sort of a subspace, right? So if I want to take the span of all of these vectors, that's going to produce some sort of a subspace. And then if I do that, I could consider this what we say an orthonormal basis. That's just simply, if I choose to use one of these orthonormal sets to construct a subspace, then the very thing that I use to construct, we can just relabel it as an orthonormal basis instead of just an orthonormal set. Okay. Now I don't want to waste too much time on this kind of a computation, so I'll give you the recipe though. Because the main one that we're going to do is a formula that takes a little bit longer. But here's this procedure. So to show that a set of vectors of some sort of finite length is an orthonormal basis, of Rn. Here's kind of the procedure. So what we're trying to do, this would be in any situation where a problem asks of you, it says, hey, can you demonstrate that a set of vectors is actually an orthonormal basis? And we can think about these steps just in terms of the definition. The first thing we need them to be, we can't even get to orthonormal without orthogonal, right? So we should probably check that they're even orthogonal in the first place and not waste our time. So let's check that they're all orthogonal. So we would want to, how do I check that all of the vectors are orthogonal to each other?
Take the dot products.
Yeah, dot products of everything. And we did a full example of that. So if you want like a slowed down hand computation example of what that looks like, the previous lecture has one of those. So we would compute all possible dot products. All possible dot product combinations of V1 through Vp. So if I only had two vectors, that's really easy, because I just take the dot product of those two vectors, and that's all the combinations. If I had three vectors, like in the example on the previous lecture, that means we need to check three possible combinations of those. And if I had four, et cetera, you just keep doing more and more. Okay, so once I've shown that they're all orthogonal to each other, then what makes something orthonormal that's distinguished from just orthogonal?
That are unit vector.
Unit. What does unit vector even mean?
The length of the vector is one.
Yeah, it's only one long. So I would verify then, that the length of all of these vectors is 1. Now there's a really slick way to do this. And the slick way is not by slamming it through the length formula, but recall that the length of a vector ended up having some relationship to the dot product of the vector with itself. And it's going to be much easier to just take the vector and take its dot product with itself. And if that spits out 1, then that means if you would have plugged it into the length formula, it would give you a length of 1 as well. And it's just typically easier to compute dot products instead of square roots of sums of squares. So that's why all we have to do is verify that all dot products I was misreading my own lines again. The concept is the same, I just started handwriting a different step. Compute v1.v1, v2.v2, so on and so forth until you've taken the dot product of every single vector with itself. Okay? And we want to verify that they are, I need all of these to be equal to what?
1.
That they all equal 1. And so when you really think about it, to show that something is an orthonormal basis is really just consisting of computing a whole laundry list of dot products. To get the orthogonal stuff, you want all your combinations to spit out 0. If I want to check that each individual vector itself has a length of 1, I do a dot product with itself. And all of those should spit out 1. So not too difficult to memorize. It's pretty straightforward if we remember the definition. There was a little theorem here that frankly is not that important, but I'll put it here. An m by n matrix, U, has orthonormal columns if and only if U transpose times U gives you the identity. What's this really saying? Is the ones that correspond where the transpose of your matrix is itself the inverse of the matrix. That only happens when you have this very specific orthonormal behavior going on. So this is a special definition. I mean, it has a pretty interesting use, because guess what's 10 million times easier to compute? A transpose or a full inverse formula? Transpose, right? So if we want to invert some of these matrices and we know that they are orthonormal columns, easy business. All you do is take the transpose. And so we like these because they're easy to invert, meaning that it's very easy to go in one direction and then reverse that direction with your transformation. And also, the lengths of everything is just 1. I mean, that's really, really easy to deal with computationally. A few rules of how we're allowed to manipulate this stuff for future reference. Let U be an m by n matrix. M by n matrix with orthonormal columns, orthonormal orthonormal columns. And then let's just pick two vectors in Rn. So I have some x, I have some y, and both of those vectors we'll just say have the same number of entries, some n entries. Then, here are three things. And these are all pretty intuitive. If I transform some vector x using my orthonormal matrix and then take the resulting vector, see how long it is. And that should be the same thing as just the length of x originally, right? If every single column is a unit vector and they're all orthogonal to each other, then this is a pretty expected behavior. This isn't saying that it spits out the same vector. It's just going to be the same length. We're not changing the length of a vector if I choose to use an orthonormal thing. Yes?
So I might say this wrong, but I remember a few lectures back that if you wanted to find the points of intersection of like ax equals b, you could need to do the c equals uy times.
Right.
So wouldn't now the intersections just would be the dot product of just the u times y, if I'm saying that correctly?
So you're basically like, if it's not going to change the length, why would I divide it by anything?
Yeah.
That's you're already you're thinking to the very last theorem of this section actually. So yes, your intuition's in the right direction. That's precisely, there's a theorem that articulates what you're asking as an actual rule.
Okay,
Yeah. So if you want to see the exact wording of it, it is the last theorem in the section for this. Very good. B, if I take ux and I do the dot product with uy, that's actually just going to end up being the same thing as x dot y. And then the only instance, the only case where you're going to have ux dot uy being equal to 0, that's only possible if and only if the vectors themselves are orthogonal to begin with. So you're only going to get 0 out of that product if your original vectors to start with were orthogonal. In other words, their dot product is equal to 0. Okay, and so then lastly we say, man, this U matrix is a really, really handy thing. Let's give it an actual name. And this is kind of where linear algebra is frustrating in terms of who came up with these terminologies. So let me write this down and then we'll split up the terms. An orthogonal matrix is a square, so this is what we're defining. An orthogonal matrix is a square invertible matrix. Invertible matrix U such that the inverse of U is just corresponds to its own transpose. Okay, so basically the very thing that we've been talking about. If I take this is kind of where it's frustrating. Why couldn't they just have called it the orthonormal matrix? Because we specifically want all of the columns to be unit vectors. So these are all of the terminology in order. We started with just an orthogonal set of vectors. That meant that those vectors themselves, their dot products are 0 to each other because they're orthogonal to each other. And then we expanded that and said, okay, let's even add on top of being orthogonal. That's great. Let's require all of them to now be unit vectors. And when we add that restriction, that's when we start calling them orthonormal. And for some brilliant, godforsaken reason, they say, now when we put the unit vectors that are orthogonal to each other, and actually put that in a square matrix, let's switch it back to saying orthogonal with the matrix. So when we talk about an orthogonal matrix, what's secretly hidden in there is the implication that all of those columns are unit vectors. You would anticipate it being called an orthonormal matrix because you're thinking, well, yeah, that's the next step. I've modified it yet again into a matrix. No can do, unfortunately. So whenever we talk about orthogonal matrix, always just kind of try not to forget, yes, the columns are orthogonal to each other. That's easy. But then the thing that's hard to remember is that even further, they're unit vectors. Okay? Yes, Tim.
So does regular U times a row reduced version of U still equal 1?
Wait, so say it one more time.
So if I'm understanding this correctly, you're for B, UX times UY equals X times Y is because U times U equals 1, correct? Or am I thinking of this wrong?
I wouldn't make that conflation. This is more just saying that because all of the columns are length 1 and orthogonal, that this is always going to happen. The proof of it is unrelated to the specific thing that you're intuiting.
Okay.
So your intuition is giving you the correct answer, but the intuition isn't the line of reasoning we want to use for the proof.
Then can you explain 2 from that side of the board?
How do I know that I can just take v1.v1 and that v1 and stuff like that?
Mhm.
Okay, so let's recall the definition of length. How do I compute the length of some vector? So if I want to compute the length of a vector v in general, I'm going to take the sums of the squares. So I'll start with the first entry, v1, and then I square that entry. What do I continue to do here?
Add v2 squared.
Yeah, then v2 squared. And then say this vector has n entries in it. How many times do I need to repeat this? N times, like for every single entry. So I'll eventually get up to vn. I'm squaring every single one of these. And then what's the last thing we don't want to forget?
Square root.
We throw our radical over everything. So this is what we meant by length of a vector. Now, let's get rid of the square root, because that's annoying. Okay? So I'm going to square both sides and eliminate the square root. And so what that's going to give me is just the length now of the vector squared is equal to v1 squared plus v2 squared plus v3 squared, and so on and so forth, until I get to vn squared, this time without the square root. But if you really think about the definition of a dot product, that's really saying v1 times v1 plus v2 times v2 plus v3 times v3, so on and so forth, until you get to vn times vn. Is that not the same as doing a dot product of the vector v with itself? Because all of these products are just corresponding the same entries. So this is just v dot v. And guess what number is the only number that's still the same after squaring? 1 and 0. But in this case with unit vectors, we have a length of 1 squared is 1. We can always check that through its own dot product. Does that help? Okay. So let's get on to the actual section we're supposed to be doing. And there were some good questions last lecture about like visualizing the concept, and this is the section that does that. It expands the simple understanding into a more general sense through a theorem. The orthogonal decomposition theorem. The orthogonal decomposition theorem. Okay. Let W be a subspace of Rn. Be a subspace of Rn. Then every single vector that I choose in Rn can be written uniquely in the form vector y can be written as some y hat plus z. We will talk a lot more about both of those vectors in the coming rest of this lecture, so don't worry. Where y hat is a vector specifically in the subspace, and z is some vector that is in W perp, okay? Meaning that, basically, that's just a fancy way of saying this is orthogonal to everything in that. So y hat is orthogonal to my z. In fact, and while I handwrite this, I want you to flip back into your notes when we gave the formula previously for projection stuff, okay? So go find that right now. Any orthogonal basis of W. Okay, you guys have that formula accessible for your eyes?
Yes.
What is it again?
Observe that you are learning nothing new. Y hat is equal to y dot u1 over u1 dot u1 times u1.
G.
But now this time we just have it in general, so it's not restricted to anything. So I do this as many times as I'm required to by how many entries are in this thing. In this case I have p, sorry. So if I have a set with p, I'm going to do it p times. So we've now made it 3 whole sections and really memorized only one formula, okay? So it's layering itself. Let that be an advantage to you as you learn and study.
Let's keep it going.
And z is equal to the y vector minus y hat. This is actually a subtle detail that's going to be really easy to forget and one that you won't want to forget, okay? So, this currently might not make a ton of sense. The formula at least is familiar, so it's maybe less uncomfortable. But now, I can finally give a much more accurate illustration here. So, I'll have you know, I spent last night trying to, or not last night, but like last afternoon, practicing drawing this. Because I'm not good at freehanding stuff, but I have a pretty good idea of how to do it now.
You got this. I believe in you.
And I think it's a very satisfying way to visualize it in an example. Okay, so I'll first clarify because I'm gonna want to use these vocabulary terms as I draw the picture, so that we're all on the same page. The vector. So think of this as continuing the theorem, right? So the vector y hat that we've been talking about. So the vector that gets spit out with this really convenient formula that looks a whole lot like what we had already been doing in the previous sections is called, and again, this should not be that big of a surprise considering what we just came from the previous section, is called the orthogonal projection. Orthogonal projection of specifically my vector y onto the subspace W, and is denoted, and we've already seen this notation, and now it's coming back in a more general sense, right? Let's say everybody repeat after me for the wording. The projection.
The projection
Onto W.
onto W
Of Y.
of Y.
The projection
The projection
of W.
of W
That was my bad, I said that wrong. The projection
the projection
onto W of Y.
of Y.
The W is what we're projecting onto, and then Y is the thing where it's coming from, of Y. Okay. So let's do some art, yeah?
Yeah.
Okay.
Art.
Now this is going to be the pinnacle
That's not it.
of my third degree in Renaissance painting.
Dang. This is good.
Oh my
Art
gosh.
degree. Good. Give him
Look
an art
at the
degree.
square.
Is that a square?
Look at the rhombus.
So this is some plane W. This is some subspace W. Okay. And so that we anchor ourselves somewhere in space, this is let's just say that this is where the origin is. This is where the zero vector lands. Okay.
What's the lift on your
Now, say I have. Here's the main concept. Like, if I can really help you guys to see this, everything in the section will just make sense. Okay. Subspaces. There's literally the prefix sub on the word subspace. So that kind of signals to us that it's not the whole space. A subspace is naturally, by definition, going to not include everything in the original space. So if I'm talking about a subspace of Rn, right, then I should anticipate that this isn't occupying all of Rn. Thumbs up if that makes sense, what I'm trying to get at here. By saying it's a subspace, what I'm trying to say is that, hey, this is completely contained by Rn. It doesn't even necessarily access all of Rn, it just can be completely housed within Rn as a space. What that means is for the vast majority of subspaces, there are always going to be vectors in the overall Rn that are not necessarily in my subspace. My subspace is kind of like the exclusive. How many of you have flown Southwest? Okay, you know what the most insulting new form of like discrimination in America is? It's a socioeconomic one, and it's the A primary list tiers. If you have A1 through 15 and spent $275 extra on your airfare, you can board the plane first. Okay, that's a specific subspace of the passengers and the customers. Okay, which means that the vast majority of the other vectors, the other passengers, aren't in that subspace of the A tier list people. Okay, who get to go in. So what we're very interested in is the relationship between the actual stuff in the exclusive subspace to stuff that's not accessible in the subspace. So let's now we're going to introduce some vector y. So that's what this y is. When I say that y is in Rn now, I'm not bounding it to be stuck in my subspace. I'm talking now generally. So let's say I take some vector. So think of the w as the subspace of our Rn, okay? And now I have a vector that is not inside. Ooh, okay? An escapee, okay? Some vector y. So vector y is in Rn, okay? But is it in my W? No, it's escaped the matrix. Okay, so it's outside of the subspace.
It's officially right.
Y is not a member of the subspace W. And so what we do is we think, okay, what is the best way I can relate objects that are not in a subspace with respect to my subspace? Okay? And the way we do that is by projection. So we say, all right, let's see if I drop this point down in the shortest path possible to get to the subspace, let's see where that lands. And so say it's about this high, and it lands like here. And so we mark like where it's hovering over in the subspace, and we say, let's now make a vector that goes exactly to the point where its shadow effectively falls in the subspace. And let's call this y hat, or the projection. Say with the projection onto W of y.
Wow.
Okay. Now, what we can see immediately is that y hat is a member itself of my subspace. Yes?
Yes.
Okay, so that means if I'm talking and can only see the stuff inside the subspace, y hat would be in there. Okay.
So this, the way you drew this is that W is flat and Y is above it, but since, this is in the physical world, how do we know where exactly to draw y onto w? Is it assumed to be perpendicular to w, the line connecting y to its projection?
Aha! I paid him to ask the question because that very naturally motivates the theorem for it. You want to know why I don't? Because I teach here. No.
That's why y'all still got
Okay.
Sociological.
So yes, you're right. What I'm doing right now is I recorded that.
It's okay, video can be edited.
So
Chinese government.
with handwriting, an example, right? I can't draw something for you of a 5th dimension overall space with a 3-dimensional subspace in 5 dimensions. I just can't do that. So the example I'm using here is that my overall thing that I'm taking is I'm looking at W, which is some subspace of R2 of R3. Okay. So your question being, how do I know which direction to go to the subspace? In this specific case, visually it looks like just a straight line orthogonal distance down to the plane. In higher dimensions, we lose touch with the actual how does that physically look. So instead of thinking and trying to rely on visual intuition, we trust that the mathematical pattern extends into higher dimensions, and that this idea of being coming from where the projection vector is on my subspace is still always going to be true.
Okay.
And so we're going to find out that the whole point of this section is that we really like this vector because it's going to point us directly to underneath where in any dimension in any space the closest approximation of y that is not in my subspace with respect to something that is at least in my subspace. Mm-hmm. This is how regression models work. We are effectively approximating y. What is the closest relationship we have to y if I'm only allowed to operate within a subspace? If I'm only allowed to operate with my objects in W, then this projection vector is going to play a huge role in approximating that because it's going to get us the closest, shortest distance away in the space to something that is not accessible using only elements from my subspace. Because when you plug into your Google spreadsheet your physics lab data, not 100%, it's not a perfect, it's not actually mathematically modeling it perfectly. And so if your computer system said, well, I refuse to print out this linear approximation regression model unless every data point is exactly perfect, you would never have any science projects, okay? And so what it's doing is it's utilizing this idea of, okay, the data is your subspace. The data is what you're allowed, the vectors you're allowed to start working with. The real thing that we're supposed to have is out here. And so we're approximating. We can call this distance something very specific. So I'm going to draw it over here because that's technically how the vector is defined, but it's the same exact height as this coming up out of the subspace here. And we call this is the one that we're calling Z. Okay, so when we were talking about the Z being y minus y hat, and Z being in W perp, think about this. Any vector that's just poking straight up orthogonally from this specific subspace is orthogonal to everything that's inside of this subspace. So, and in Calc 3, remember when I had you put your pen on your notebook and said, no matter where I slide this around on that notebook, it's always orthogonal to anything that lies on the notebook. In very similar sense here. So Z, that's what we mean by Z is in W perp. It's just, it happens to be exactly and definitionally perpendicular to
So Scott,
W.
this is a bit off, but so the vector Z is the distance from y hat to y vector?
Exactly. This is if I took y and I subtracted from it. Y perp. Right?
That's why it's a projection of. Oh, wait a minute.
Okay.
So I got a question. If it's a plane.
This is just a specific, it's not always a plane. This is the only thing I can draw to you that you can see with your eyes, and that I can draw with my hand. Okay.
So this is a weirder question. So, is there a way to plot regions of the three-dimensional space by Z being perpendicular to the, how can I explain this? perpendicular to the plane W. Like for example, if the plane was curved by Z being like perpendicular to the plane, wouldn't it be possible to like make like a triangle of like the projection of it?
What you're describing is something that is covered in Calculus 3, where we learn how to define normal vectors to surfaces. So for any type of surface that's in space, we could define what it means to be normal no matter where you are on that surface. So go back to, I can't remember who took that class yet, but it's in 17.6 or something like that, where it actually talks about how to explicitly construct what you're talking about. But yes, that is possible, and that does exist, just in a different class. Okay, so does it make sense that if I said that Z is in W perp, does this now have a much more concrete understanding of that statement instead of it just appearing in the theorem statement?
Yeah.
Okay?
Makes
That's
sense.
what's going on here. So,
No.
now think for a second. Just an observation. An observation that you can make from this that ends up being a formal theorem statement that I won't waste your time on because you can just look at it. If the vector y itself was actually something that you could access in the subspace, then your approximation ends up being perfect, right?
Wow.
Because the very thing that you're projecting onto, there is no shadow. You are on the ground, like where you are supposed to be. So if y itself is actually in your subspace, you could get to it. Then imagine trying to do like a projection. If there's nowhere to fall onto, you are simply where you're supposed to be. In other words, the vector itself is its own projection. If you're lying exactly where you're supposed to be, then you're already there. So that's when the projection, everyone say, the projection onto W of y just corresponds with the actual vector itself. Okay? That only happens, of course, if the very thing you're trying to get to is already something that you could access in your subspace. Okay? How do we feel about this? When we do a formula and actually compute one of these by hand, now you have a motivation for what you're actually hand computing for. When you're given a starting orthonormal basis, when you're given some vector y that's not necessarily restricted to your subspace, what you're doing when you're doing this formula is you're finding precisely the very vector that will always, by definition, land you exactly at the closest possible distance away from that vector y. You're getting the most accurate approximation with respect to that subspace that you have of whatever object that you're trying to get to.
Is there a map where it'll be better to state y vector as projection on the plane W of y instead of just the y vector?
Well, yes, that's what you're stating is actually the motivation behind creating best fit lines. So like when you go into Excel and you have your data that's not perfect, but it can still magically produce for you a line and an equation for that line, what it's doing is precisely that. It is more convenient sometimes to use the approximated value instead of the exact value, because the exact value isn't even possible to get to using your data set that you have. Okay, so let's actually do an example with the computation so you can practice putting these dot products together, but it's really not that hard. The hardest part is understanding this picture. The hardest part is understanding what the characters are, how they're interacting with each other, because now if you really get that and review that, word problems of this topic are not going to faze you really that much. Because what makes linear kind of hard is that there are approximately 10 different ways you could word exactly the same problem. And you could articulate what you're trying to do in your problem probably 5 or 6 different ways that all sound very different. But in reality, you're doing exactly the same procedure. So that's why familiarity with this is going to help you not feel like you're learning 10 different procedures. It's all one procedure, but different permutations of the steps involved with these guys. Okay? Example. Let u1 be equal to 2, 5, negative 1. u2 be equal to -2, 1, 1. And then the vector that is not in our subspace is 1, 2, 3. Now you might be thinking, hold on a second, Scott, those are all in R3. They're all in the same subspace. Not necessarily, because if my subspace that I want to have, W, is the span of only U1 and U2, you can verify separately that the span of these two vectors does not include Y. You can't get to Y using linear combinations of this. What's another way of saying that? If you were to set up the linear system, if you were to set up the system of equations with the matrix equation where you put 2, 5, -1, and -2, 1, 1, and try to augment that with 1, 2, 3, guess what you're not going to have? A solution. This doesn't have a solution. This system of equations cannot be solved. So what do we do about that? Does that mean we completely throw it out and never consider these situations?
Yes.
Well, that's the pure math answer, actually. But
There you go.
the engineers kind of needed help with their little lab experiments, so we decided to build them some stuff. Okay? So, the main thing I want to emphasize with this example, these two vectors, the span of these two vectors does not include Y. Few observations. Do not fall into the trap that just because they have the same number of entries necessarily means that they are in the same space. Okay? Y fails to be accessed by any linear combination of my two vectors. Meaning that if I want to figure out how close I can get to Y as a linear combination, what's the closest linear approximation of Y?
The projection on
The projection, using the formula, okay? For fun and for review, we can verify that U1 and U2 are in fact orthogonal to each other.
by doing dot product.
U1 dot U2 is equal to 2 times what?
-2.
Plus 5 times what?
1 plus -1 times.
Right, plus -1 times 1, and that is 0. -4 plus 5 and -1, so you have -5 plus 5. Okay, so are they orthogonal?
Yes.
Yeah. Okay. So they are an orthogonal basis, and then now, say you were asked to do this. Here's one of many ways this problem type can be worded for you. Do not think this is the only way. This is one of like 4 alone in just the section. Okay. Write the vector y as the sum of a vector y hat in the subspace W and a vector z in W perp. You see something like that and you think, oh my goodness. The word approximation doesn't appear in there. The word projection vector doesn't appear in there. Does that mean it's a different concept? No. Just because we can state the same stuff in 10 different permutations doesn't make the actual concept any different. This is still the same, okay? And so when I set this formula up, I think, okay, well, to find my y hat, which will be guaranteed to be in my subspace, y hat is equal to, I know you have it somewhere in your notes, so I'll let you tell me the formula.
Y
Times
dot U1 times U1 plus.
Why am I adding more terms to this?
because there's an R3.
Yeah, because there's another vector to accommodate for, okay? What goes here?
Y
dot U2 over U dot U or U2 dot U2 times U2.
Do I keep going?
There's
Why do I stop?
no vector.
Yeah, because that's it. I mean, you have U1, U2. So, just because it's very tempting, because your formulas are given to you in general terms, like n terms, that doesn't mean every application is always just, don't copy paste your logic on that, okay? So always be sensitive to the context of your problem. Okay, you know how to take dot products. And guess what you also know how to do? just scale a vector using a constant multiplier. So from here, you actually can do this problem and it's done effectively. There's no new concepts. There's nothing different here. What time is it? 01. Do you want to see the arithmetic?
Yeah.
Actually, it's 2:02. Here's your exit ticket. Produce the solution to this question, and then you can go. How about that?
All right.
Don't forget that you also need to produce your z, which is, by the theorem, y minus y hat.